Welcome back to Electron Devices and Circuit lecture video series. In this video, we are going to discuss about the topic Enhancement type MOSFET.
After watching this video, you will be able to understand the structure, operation and characteristics of N-channel and P-channel enhancement type MOSFET and comparison between the different types of transistors like BJT, JFET and MOSFET. We will see this one by one. First one is the N-channel enhancement type MOSFET. Let us first learn about the construction. So in the N-channel MOSFET, the P-type material is used as a substrate and N-type semiconductor material is used for forming the channel. And the gate terminal is taken with the help of metallic contacts. And the SiO2 layer physically separates the gate terminal from the P-type substrate. So with the help of metal contacts, the drain terminal is taken directly from the N-type semiconductor material. So all the three terminals are taken with the help of metallic contacts. And another terminal called substrate terminal. This terminal is internally connected to the source terminal and a common terminal, a single terminal is brought out from the source terminal. So this is the construction of enhancement type MOSFET. When you compare this construction with the depletion type of MOSFET construction, see here in the depletion type there is a physical existence of channel between these two P-type material. This is a P-type channel. So there is a physical existence of channel here. Whereas here in the case of enhancement type MOSFET, there is no physical channel exist here. So that is one of the main difference between the enhancement type and depletion type of MOSFET. So this is the symbol of enhancement type of MOSFET. So here in most of the cases, so the this is the substrate terminal, drain, source and gate terminal. Most of the cases the substrate terminal is connected to the source internally and a single terminal can be brought out, that is called a source. Whereas in case of depletion type, this is considered to be a continuous line. Whereas in case of enhancement type MOSFET, this is a discontinuous line. So here the drain terminal separated and again the substrate terminal physically separated between the source terminal also. So the main reason is since the channel does not exist permanently between these two type of semiconductor, this is represented by a splitted line here. So this is the symbol N-channel in inward arrow. So this is the construction of N-channel MOSFET, right? We will go for the operation of N-channel enhancement type MOSFET. So normally enhancement type MOSFET operates in only one mode, that is called as an enhancement mode. Whereas depletion MOSFET operates in two modes, enhancement mode and depletion mode. Let us see why the depletion mode operation is not possible here. So here also the operation can be analyzed in three cases. Case 1, VGS equal to 0, VDS is applied and VGS negative and VDS is applied. VGS positive and VDS is applied. First case, VGS is equal to 0. If VGS is made as 0, so here the third terminal is considered here. This terminal is internally connected to the source terminal and this is taken out as a single terminal from the source, that is grounded. And as VGS is equal to 0, so VGS gate terminal is connected to the source terminal, short circuited. In short circuited path, voltage equal to 0. So VGS is equal to 0 here. Now let us see when VDS is applied alone, what happens. So VDS is applied here. So if VDS is applied, so this is an N region. Normally the drain terminal is made or connected with the reverse bias voltage. So this is negative terminal. So this is connected to positive terminal of VDS. So drain is positive with respect to VDD and the negative terminal of VDD is connected to the source terminal. So source terminal is in forward bias and drain terminal is in reverse bias, and as a result of which, let us see what happens here. So here due to repulsion, more electrons from this N regions are pushed to move towards the P region. But since there is no physical channel existing here through these two N regions, there is nothing but the P-type substrate. In the P-type substrate, majority carriers are holes and at the same time the PN junction is created across this N region and another PN junction is created across this N region. So due to the presence or due to the non-existence of channel between these two regions, these electrons that are repelled from this N regions cannot get cannot get enough force to enter into this N region. So whatever may be the value of VDD, these electrons cannot acquire enough strength to enter into these electrons does not acquire enough strength to enter into N region, and as a result of which no current flows through the drain terminal. So because of this reason, the drain current becomes a 0. So whatever may be the value of a VDD, without the application of a VGS, no current flows through the FET. Hence, this type of MOSFET is called as a normally off MOSFET. Normally off MOSFET. So without the applications of gate source voltage, drain current becomes 0. So this is the reason why it is called so. So first case is of useless. We can't able to use the device in this case. So this case is not possible to use. Hence we can go for case 2. VGS is negative and VDS is applied. So VDS is applied. So we have to apply VDS along with VGS. So initially, first we will see by applying the VGS alone. So VGS alone is applied. So VGS is taken as positive voltage. So if a VGS is positive, so what happens here means, so for the positive VGS, this gate per terminal becomes more and more positive, and as a result of this positive force, here the p-type substrate is there, which is having majority carriers holes and minority carriers electrons. So these due to the force of these holes, the holes which are the majority carriers in p-type are pushed towards the substrate, and as a result, the minority carriers electrons acquires enough strength from this positive terminal and starts to move towards the positive terminal due to the force of attraction. So while it is moving, so here the electrons are moving in this direction, holes in this region are moving in this direction. So due to the movement of these electrons and holes, the recombination takes place. If the value of VGS is less, with this recombination itself, all the holes, all the minority carriers, that is electrons, get wasted in the recombination, and as a result of which this minority carriers cannot contribute for current conduction. Now if the VGS value is increased, now what happens if the gate terminal is having more and more positive, now the force of attraction of this gate terminal towards the minority carriers electrons in the N-type increases. Now more and more number of electrons, minority carriers from the P region starts to move towards the gate terminal. Now this electrons, minority carriers acquires enough strength from this gate potential, and it can able to overcome the recombination with the holes, and we can able to accumulate near the SiO2 layer, that is an oxide layer. So the electrons starts to accumulate near the oxide layer, and now if the amount of VGS still increases, still the strength increases, and as a result it can attract more minority carriers here. The minority carriers electrons acquires more strength, so that it can able to overcome the recombination that is taking place with the electrons in this region, and it can come out from that of the recombination and gets accumulated towards the gate terminal. It cannot cross SiO2 layer, so it gets deposited near the oxide layer, and once if it gets a sufficient amount of accumulation, this establishes a channel, because this is nothing but electrons accumulation. This is an N-type material. So once if the path is created by the electrons between this N region and this N region, the channel is getting created. So why it is called inversion layer? This channel is called as an inversion layer. Why it is inversion means, this is a layer of electrons that is created in a p-type substrate. So p-type substrate, N-type layer is created, N layer is created. That's why it is called inversion layer. This layer is responsible for allowing the electrons to flow from source terminal towards the drain terminal. Right. So now here the drain source voltage is not given, so the circuit is not closed. Even though the inversion layer is created, the electrons cannot flow, come out of the drain terminal. So to get the current flow in the FET, we have to supply a drain source voltage. Right. So the minimum value of a VGS which is required to establish a channel in the p-type substrate is called threshold voltage. Right, threshold voltage, the minimum value of a VGS which is required to establish a channel or inversion layer is called as a threshold voltage. right? So that and after that how the current will flow means we have to apply the drain source voltage. Let us see here. So now the drain source voltage is applied here. So always the drain terminal is in reverse bias. So this is an N channel. So this is drain terminal is made positive. So this is positive. So the electrons initially with the help of this inversion layer here repulsion is there. So here negative. So the source is negative. So repulsion. So more electrons starts to move towards the this regions, and as a result of this inversion layer, electrons can move freely through this layer and enter the end region. Now if the drain source terminal voltage is applied, so the electrons that is accumulating in this end region starts to move freely towards the positive terminal of the battery, and as a result the current starts to flow in this direction. That means from the negative terminal of the battery towards the source, and again from end region through this channel, this end region, and through metallic contacts, so drain terminal, and again the circuit is getting closed like this. Right now if I am increasing the value of VDD, what happens means, so now the VGS is taken as threshold voltage, because this VGS is responsible for creating the channel. Now I am not disturbing the VGS. VGS is kept constant at threshold voltage. Now I am increasing the value of VDD from 0 to maximum value. So initially if VDD increases, so this is in reverse bias and this is in forward bias. So with the help of this forward bias, the depletion layer width here is less compared to that of this depletion layer width, because this is in reverse bias. Depletion layer width increases, so this is acting as a resistance region, so that reduces the effective width of the channel towards the drain terminal. So see here, the width of the channel towards the drain terminal decreases because depletion layer increases, whereas that will not happen in the source terminal because this is in forward bias. So depletion layer width will be very less. So and now still if I am increasing the value of VDD, initially the current flow increases, and after that once if the channel width decreases, and if this happens continuously, so the pinch off condition will take place. That means this channel get completely detached from this end region. So even though if it happens like this, but due to the strong force of this electric field, the electrons can able to enter into the end region from here to here through this discontinuous channel also, and the circuit get closed, electrons move towards the positive terminal. But under this condition the current flow cannot increase, it remains saturated, right? So still this pinch of voltage, till the channel is having a continuity, the current starts to increase. But if we increase the value of VDS, the depletion layer here increases, so effective width of the channel decreases. So from this end region to this end region, channel continuity will not be there, even though the electrons can able to enter into this end region, but this will not contribute for increase in the current. Whatever the electrons that is available here, those electrons alone can take part in conduction. So it will not increase the number of electrons. That's why the current got to attain the saturation condition. So this is the thing happens if we increase the value of VDS. Now if I am increasing the value of VGS again and again, so here this here the channel formation will be getting on increasing, and as a result the drain current increases. But if I am increasing the value of VDS, the drain current attains a saturation value. So this can be observed in the characteristics curves like this. So this is the here VGS equal to 0 condition is not there. So the MOSFET starts to conduct only if the VGS voltage is greater than threshold voltage. Here threshold voltage is taken as 3 volt. And if VGS 3 volt or greater than 3 only, the MOSFET starts to conduct. And if I am increasing the value of VGS, see here the drain current starts to increase. This is because the channel width of the channel that is establishing between the two end regions increases. So accumulation of electrons in the channel increases. So it increases the drain current, and this is the enhancement mode of operation. And this saturation happens after the pinch off voltage. So we can say here this voltage is the pinch off voltage. This voltage is the pinch off voltage. Pinch off voltage is the voltage, that is VDS voltage, at which the channel physical continuity of the channel get disturbed, and the current starts to remain constant. And this region of operation is called ohmic region, and this region is active region, and this region of operation is called cutoff region, because for what value of VGS less than 3 volt the transistor is said to be in off condition, so we can say that is the switch cutoff region. And this is the drain characteristics of MOSFET. So the MOSFET, similar to that of JFET, MOSFET can be operated in 3 regions: ohmic region, saturation region, and cutoff region. Got it? It is capable of operating only in enhancement mode. If we apply a positive negative value of VGS, this will not work. The next characteristics is transfer characteristics. By taking VGS on the x-axis and ID on the y-axis, if we increase the value of VGS till it reaches the threshold value, the drain current becomes 0. This is because the channel will not get created between the two end regions, and hence the drain current 0. If we increase the value of VGS beyond the threshold voltage, the current starts to increase exponentially. This is because the width of the channel increases, as a result of which the drain current increases. So this characteristics can also be obtained theoretically by using this theoretical equation IED equal to K into VGS minus VGS threshold whole square. So in this equation, K depends on the value of physical parameter of the device, that is an constant value. So from this characteristics, we came to know that in active region greater than threshold voltage VGS value, we can able to use the transistor as an on switch, and if VGS is less than threshold, it has no current will flow through the device, so it acts as an off switch. And in this region, it can be used as an ohmic region, because in this region, if V increases, I also increases. Right? So this is an operation of N-channel enhancement type MOSFET. Let's discuss about the P-channel enhancement type MOSFET. So first we'll learn about the construction. Here the substrate is formed by N-type material, and the P-type material is used for the formation of a channel. And here the gate terminal is taken from the metallic contacts, and this is the SiO2 layer that physically separates the gate terminal from the N-type substrate. And the drain and the source terminals are directly taken from the P-type material through the metallic contacts. So all the 3 terminals are taken with the help of metallic contacts. So the substrate terminal is directly connected to the source terminal. And see here, so there is one corrections here. So this is neglected, right? So the substrate terminal is connected to the source internally, and a common terminal is taken out, and that is called as an source terminal. So this construction is somewhat opposite to that of the N-channel enhancement type MOSFET. So this is a symbol, only difference is arrow is coming in the outward direction when compared to that of the N-channel. See, the next one is and this is the operation of a P-channel enhancement type MOSFET. You know that enhancement MOSFET operates only for enhancement mode. In P-channel, enhancement mode is possible for negative value of VGS. Let us see how this is happening. When we apply the VGS alone, so initially compared to the previous one, similar to previous one, when VDS voltage alone is applied, due to the non-existence of channel between these two P region, current conduction will not take place, so drain current remains 0 and transistor is said to be in off condition. And now if we apply the negative value of VGS, this gate terminal is negative, so with the negative force of gate terminal, it repels the electrons that is present in the N-type substrate, and all the electrons present here are pushed towards the substrate terminal, and now the minority carriers in N-type substrate, which is the holes, are start to move towards the gate terminal, because gate is with negative potential. While these electrons this holes starts to move, and this electrons starts to move towards the substrate. Both are in opposite direction. While moving, it tends to recombine, and due to recombination, all minority carriers get lost for low value of VGS. If we increase the value of VGS, and if VGS is equal to threshold voltage, now the minority carriers holes moving towards the gate terminal can able to overcome the recombination, and it can reach the or near the oxide layer, and it forms a deposition layer of holes near the oxide layer. And if we increase the value of VGS further, more and more accumulation of holes takes place near the oxide layer, and this results in the creation of inversion layer. So this is the this is a layer of holes in the N-type substrate. So that why it is called as an inversion layer. The presence of inversion layer now provides the path for the charge carriers to flow from source terminal towards the drain terminal. At this instant, now if we apply a drain source voltage, see here the drain source voltage, the drain terminal is always in reverse bias. So this is taken from P-type, so that has to be connected to negative terminal. So due to the reverse bias, the holes that is starting to move from the source towards the drain terminal, all the holes are moving towards the negative terminal of the VDD, and this results in the flow of current like this. Right, the current is the flow of holes starts to constitute circulate like this. And if we fix the value of VGS equal to threshold voltage, and if we increase the value of VDD, the same thing happens as such in that of N-channel enhancement type MOSFET. If we increase VDD, the depletion layer width on this P region towards the drain terminal increases, whereas this depletion layer on the source terminal decreases. It remains the somewhat, it's not that much high compared to that of these things. So as a result of which, the effective width of the channel near the drain terminal decreases, and at one particular value of VDD. So till that particular value, the current starts to increase towards the drain terminal, and once a particular value called pinch off voltage is reached, at that particular value of voltage, the physical channel get completely separated between these two P regions, and as a result of which, even though this channel got discontinuous here, these holes that is present in the channel acquires enough strength with the help of this electric field, and still they can support for current conduction, but it will not contribute for increase in the current. So that's why this current remains constant after the pinch off voltage. Once if the channel path gets separated, after that if we increase the value of VDS, the current will not increase. This remains constant. This is because with the support of this electric field, the electrons can simply jump from this channel towards this P region due to the attractive force of this P region, but it cannot contribute for increase in the current. That's why it remains constant. So after that, so this region of operation we call it as saturation region. After that, if we still increase the value of VGS, so now the more accumulation of holes takes place near the oxide layer. So this contributes for increase in drain current, and after that if we increase the VDS, the same thing will happen. So this can be observed from this characteristics. So see here, so the VGS, so here the VGS is negative, so the threshold voltage is taken as minus 2 volt. So till it is till the threshold voltage, VGS is taken as minus 2 volt. Till it reaches minus 2 volt, the current becomes 0. And after minus 2 volt, so minus 3, minus 4, minus 5 like that, the drain current increases. And this voltage is called as an pinch off voltage, similar to that of N-channel MOSFET. So this voltage is called pinch off voltage, and after this pinch off voltage, the current remains constant. And this region is saturation region, and this region is ohmic region, and this region is cutoff region. So, and the next is transfer characteristics. VGS on x-axis, ID on y-axis. So here VGS is negative, so I am taking the second quadrant, and ID is opposite, so this is negative. So this is opposite to that of N-channel. So this is negative current. Till it reaches the threshold voltage, this current remains 0, and after threshold voltage, current starts to increase exponentially. Right, the same expression what we have discussed in P channel, that is N-channel, this expression is suitable for P channel also. So this is the operation of N-channel and P-channel enhancement type MOSFET. So the next, this is just an overview to have an easy remembrance, that just transfer characteristics alone. This is the symbol and corresponding transfer characteristics. And this one is the overall all four things, that is N-channel, P-channel enhancement type, and N-channel, P-channel depletion type. So only one difference may be here in the transfer characteristics. So while I am representing the transfer characteristic, here it is taken as minus ID. Whereas what they did is ID is minus ID means it has to be come in this side. So this characteristic shifted to this third quadrant. So that will be the difference when you observe this characteristics. So all drain current, if it is positive, means taken in this direction, negative means opposite direction. Correspondingly, voltage and current polarity, the quadrant gets shifted in this curve. So this is also correct, and this characteristics also correct, provided if you represent the drain current negative here. So, and the next one is the comparison between the different types of transistors, BJT, FET, and FET means JFET, and then MOSFET. So device type BJT non-current control device, FET is both are voltage control device. This is bipolar device, these two are unipolar device. Terminals, it cannot be interchanged. Here these terminals can be interchanged because a drain and source terminal can be taken from the same type of semiconductor materials, so it can be interchangeable. Operation modes, it cannot be operated in different modes. It can be depletion, JFET can be operated only in depletion mode. This can be operated both in depletion mode and enhancement mode. Input impedance, this is low, whereas this is somewhat high, and whereas this is very high due to the presence of SiO2 layer. Output resistance, it's somewhat greater than 750. This is greater than 10 mega ohm. This is greater than 10,000 mega ohm due to the presence of SiO2 layer. Operational speed is, this is low, this is somewhat moderate, and this is very high. Because of this high switching speed only, it is almost preferable in all industrial applications. And the noise is also, this is very low compared to that of BJT. Thermal stability is, this is very high. That means whatever may be the changes in the temperature due to heat dissipation, it will not affect the functionality of the device. That's why we can say stability will be very high. Thermal stability means stability with respect to temperature. And the channel existence, it is our main thing. So there is no channel in the BJT. Whereas some physical channel, in FET also the channel exists permanently. Permanently the channel exists till the entire operation of the device. Whereas in case of MOSFET, the channel exists permanently in depletion type or D type, but not in enhancement type or E type, because only after the application of threshold voltage, only if VGS greater than threshold voltage, the channel got created. Below that, there is no physical existence of channel. So this is the comparison of three types of transistor. So keep it in mind. Hope at this juncture you got a clear understanding about the operations of different channels and different types of MOSFET. So have a good understanding by repeatedly watching this video. See you back in the next video. Thank you.